So the setup of our discussion for PCA is this, that we have independent and identically distributed data set X made of points x1, xn, and this is really a set of d-dimensional vectors. And we have that, we are looking for m-dimensional data space given by a set of basis vectors, b1, bm. So these are d-dimensional vectors, and they are orthonormal, so orthogonal to each other and of norm 1. And we are looking for these projections defined by, so let me just define B directly in terms of a matrix. So I'm going to just make the point that this is a matrix formed by these column vectors B1, Bm, and the projection Zn of point xn is simply given by this multiplication, is the B transposed matrix times xn. So these are going to be the projections. Onto the subspace spanned by vectors b1, bm. And remember that we had already in the last video this data covariance matrix defined to be 1 over n, sum of the inner product of all these points, so xn times xn transposed, and this is a d times d matrix. And so one point we have made last time is that we are going to assume our data points to be of mean 0. So, and I want to come back to this point and really show you that this is fine from the point of view of what we want to achieve. So assume that the mean of x is 0. Now, if this was not the case, if the mean was mu, then really what we would essentially do, we would subtract mu from each one of these points so that we get a new data set with mean 0. And if we are taking the variance of these data points, so the variance of z, where z would be really defined as a projection of the transformed data points, the ones that we are making so that they have mean 0. So this one, if we take into account this translation, this would be equal to the variance of, and I'm just calculating this one to be B transposed X minus B transposed mu, and that's essentially a constant. So the variance is really that one of B transposed X. So in other words, if the variance is the thing that is really driving our reasoning, then working with B transpose X or working with B transpose times X minus mu doesn't make any difference. And just to make our notations, our formalization of the problem easier, we are going to assume that we already have mean 0. If we didn't, we would have to work with X minus mu instead of X, and it really doesn't make any difference from the point of view of variance. So that's why this assumption that the mean is already 0 is fine for our mathematical discussion. In a couple of lectures, I'm going to come back to this point and discuss what do you do in practice when in fact you will have data points with a mean that is non-zero. And so we will come back to to this point at that point. But for now, it's safe to assume that the mean of our data points is 0. And what I want to do in this video lecture is really to extract just one single vector. So I just want to find one single direction, one single vector, if you like, that's going to really preserve the variance as large as possible. And I want to make this point on the next whiteboard, but I just focus for now the discussion on one single vector, and in the next video lecture I'm going to expand the discussion to how to find all the basis vectors up to m, but for now the discussion is going to be just one single vector. And here is how you should think about this. Let's say that you have this data set, and I just essentially replicated this data set 4 times on this whiteboard. And you can think about PCA from the following perspective. So PCA is just about eliminating some of the dimensions of these data points. And as they are given to you in this example, they have 2 dimensions. So you're going to really compress them, and you're going to think to start with on just one single dimension. So you would say, what is the one dimension that's going to preserve as much of this data set as possible? In our example, because we have 2 dimensions, so we think about one dimension. So that means that we are thinking about one line in this space onto which, if we project our data points, we are going to preserve as much as possible from these data points. And I just want to reason with you, what is that you want to preserve as much of as possible? So if I take, for example, the following line, and I say, I'm not sure, but how about if this was my line? And you would say, fine. So as a projection on this data, on this line, this point corresponds to this. And this point corresponds to this, and this point corresponds to this, and this one corresponds to this, and maybe this one will correspond to this, and this one will correspond to this. And when you look at this, you realize that maybe you haven't done really as good of a job as you could, because your original data points were quite spread out. If you think about the distance between them, there were some points that were nearer each other, and there were some points which were really far away from each other. But when you do this projection, you see that in fact they are kind of compact, your projections. They seem to be onto each other quite much. So this idea that there was some variance between and some distance between your original points and not so much of a distance between the transformed data points, that's one idea that we should have, that maybe we should preserve more of this variance, of this distance between the data points. And this is really a function of how you select your line. If, for example, you say, well, how about if I select something else? I will select maybe, this one. And then you say, fine, so this point is going to be here, and this point is going to be here, and you will say, well, this one here, and this one here, and this one there, and this one will be projected there. So your data points, the blue stars you had in the beginning, they are going to be replaced by these orange dots. And in some sense, this is now looking better. There is a little bit more of a spread out than what you had in this example. But still you see that this is maybe not as satisfactory as you would hope. They are still, this idea that some points are really quite far from each other, you don't really see that in here. The relative distances seem to be quite close to each other. And so you are pushing now this idea, and you say, well, how about if I choose, this line? And you'll say, fine, I'm going to select this, the projection of that point is this one, and then I have this one, and this one happens to be exactly on the line, so that's the projection, and this one in here. And this is now getting already better. You see, the points are even more spread out than what we had in the previous example, so we are getting even closer to the idea of preserving the variance, preserving the spread out of this data as much as possible. And after some reasoning, you might realize that in fact the line that preserves most of the spread out and most of the variance will be something like that. And when you project them, you are going to see that indeed they are quite spread out in this line, and in some intuitive sense that I'm going to formalize in a moment, they are as spread out as you possibly can get them on a single line as the initial data was. And so this is the intuition that I would like to work with. In general, for a given data set with d dimensions, I would like to find just one vector, one single vector, that's going to preserve the variance of your initial data set as much as possible. So that's the maximum variance perspective, and this is about finding the direction with the maximal variance. And we can formulate this problem in the following way. So we are looking for a vector, just one single vector for now, and that's a vector over r to power d that maximizes the variance of the projected data. And so what this means is that really you are going to take the projected data, and that's you are going to take the variance of the projection data. So that's the variance of say z1, and it's z1 because it's really the projection onto this vector b1. So if I denote this by say v1 to be this variance, so that by definition is 1 over n, sum of all the projected data points, z1n squared. And remember that this z1n, the way you get it is really b1 transposed times xn. So, and this is you do for all the data points. And so with this insight, then we continue our calculation. The variance is going to be 1 over n, sum of, and instead of z1n, I'm just putting this one. So it's going to be b1 transposed times xn, the inner product of these vectors. And that is equal to, and here I have one argument for why. I'm going to explain the argument in a moment. So this is going to, I'm going to rewrite this as sum of, and then on one hand I have exactly what I had before, b1 transpose times xn. Maybe I put it like that, times xn transposed times b1. And the argument here is that the inner product satisfies this property. So this is true in general because it's just a product. It's a sum of the products of their components. So it doesn't really matter which one you list first. And this is really easy to check, and you can also see it from chapter 3 of our textbook. And so when I'm doing it like that, what I get is that it's I can take, I'm sorry, this was b1. So I can take b1 transposed and b1, so this one to the left of the sum and b1 to the right of the sum, because the sum is really over these xn's. So what I'm getting is that is b1 transposed times 1 over n sum of xn times xn transposed, and here multiplied by b1. And this is nothing else, this one, than the covariance matrix of your data set. So what you get is that the variance that you want to maximize is exactly b1 transposed s times b1, where s is the covariance matrix of your data set. And so you want to maximize this, and obviously you realize here that for this vector b1, if you take the amplitude of this vector larger, you are going to get larger variance, and that's not really what you're interested in. What you're interested in is mostly the direction, not really the amplitude of this vector. So we are going to really assume a normalized setup. So assume a normalized setup. Meaning we're going to assume that the norm of our vector is exactly 1. It doesn't make any difference if I take it larger, I'm just going to inflate this variance, but the problem of maximizing the variance is really about finding the direction of this vector and not its amplitude. So we're going to work always with vectors of norm 1. And so the problem that we want to solve is we want to maximize this quantity. So the problem to solve is we want to maximize B1 transpose S B1. So we want to find the B1 that maximizes this one, where S is given, is the covariance of your data set. And this should be subject to the norm of B1, or the norm squared, if you like, is equal to 1. So what we have in this problem is really a constrained optimization. And there is a technique for solving such problems. And you can see it in a textbook in the background part. You have a discussion in chapter 7 about this. But also you might know this from other courses, that this is solved via the Lagrangian multiplier. And the idea of this Lagrangian multiplier that I'm going to write in just a moment is that from a constrained optimization problem, the Lagrangian multiplier leads to an unconstrained optimization. And the point with the unconstrained optimization is that you can then use calculus and take, partial derivatives and all that thing, which is going to lead quite fast to a solution. So this idea of the Lagrangian multiplier is a general technique for solving constraint optimization problem. So when I'm writing the Lagrangian multiplier for this problem that you need to solve, the Lagrangian is going to be, it's always a function of the vectors that you want to optimize over, and it's also introducing one Lagrangian multiplier for each constraint you have. And by definition, the Lagrangian multiplier is going to be exactly this function that you want to maximize. And then you always add this additional factor, which is lambda times, and this is going to be 1 minus this constraint. So it's going to be 1 minus this norm squared, which is nothing else than B1 transpose B1. So you are going to now look for the properties of this Lagrangian multiplier. And the insight that you have, and this is being discussed in chapter 7 and also in any course that deals with optimization problems, the idea is that solutions of this problem you have, they are going to be local optimum points for this Lagrangian multiplier. So it's going to be a necessary condition for a solution to the problem to be among those on which the partial derivatives of this Lagrangian multiplier are 0. So that leads directly to the idea that we will calculate the partial derivatives of this multiplier, of the Lagrangian multiplier, with respect to B1 and to lambda. And when we calculate it with respect to B1, we get, this is the quadratic term in B1, and so when we take the partial derivative, we get 2 B1 transposed times S, and we also get here one quadratic term in B1, and when we take the partial derivative of that one, is going to be minus 2 times lambda times B1 transposed. And then when we take the partial derivative with respect to lambda. This term is constant, so that disappears, and it's just this part. This is the linear term in lambda, so it's going to be 1 minus b1 transpose times b1. And so we are putting this to 0, and from this one we get right away that b1 transposed b1 is equal to 1, and from the other one we get that S times b1 is equal to lambda b1. And what we realize here right away is that just by thinking about eigenvectors, eigenvalues, these are being discussed in the textbook in chapter 4, and you certainly have had this in other courses as well. But if we embed this problem that we need to solve in terms of eigenvectors, eigenvalues, what we realize is that we have, so the B1 is eigenvector of S, and lambda is its eigenvalue. And so this eigenvector idea leads us to think about the following idea. So this was all about maximizing the variance, and the variance was exactly B1 transposed S B1, and this is I'm sorry, there is a mistake here. This is B1 transpose B1. So S B1, this is equal to lambda B1. So we are getting this is equal to lambda B1 transpose B1. And now B1 transpose B1 is 1. So this is equal to lambda. So maximizing V1 is all about maximizing lambda. And remember, lambda is an eigenvalue of S. So that's about maximizing or choosing. So choose the largest eigenvalue of S. So there you have it. The whole idea we had in the beginning that we have to select the direction on which when you project your data, you are going to get maximum variance. It's all about taking the covariance matrix and choosing the largest eigenvalue of that matrix, and that's going to give you the eigenvector that you should really choose as the direction of the line on which you project the data points. So with this idea, if you want to write it like this, it's going to be from a point X, you are going to get into B1 transposed X. That's going to be the projection. And then if you want to go back to your original data set, this would be about B1. So this was Z equals, and this was B1Z, which is B1 transposed X, and there you have it. That's how you go from the data, the original data, to the compressed form, and then back to the original dimensions you have. So with this, we are ending this lecture with the key insight that if you just want to select one single line onto which projecting your data preserves the maximum of the variance of the original data set, this is all about looking at the covariance matrix, choosing the largest eigenvalues it has, and that eigenvalue will lead you to the corresponding eigenvector, and that eigenvector is the one that you want to choose as the direction of your line.